Alan?
I do not do it. I was in the process.
Okay, that's okay. I was just trying to, if anybody else is doing it, we want to make sure we like what our data is. Alright? And so now with that data, once you convert your feet into meters,
that's 46.34 meters.
46.34 meters for the whole thing.
Yeah.
Okay. And then we're going to get meters per second as our wave speed. What's the latest you can stay, Ryan? Absolute latest.
Absolute latest, probably 11.
11. Okay, so at 10:45, we're going to allow you to begin to walk to your car. All right. Do we have a wave speed? Yet.
So we get the 38 times 4.
He did, no, yeah, I can write it up here. No one said it to me, so.
But why are we multiplying by 4?
140.
Because the wave goes back and forth as you're...
Oh, gotcha.
Because we made 4 trips, right? So.
Wait, but.
Yeah.
And the total time was between the 4 trips, right?
Is one
Yes.
back considered
So
to
you
be...
sent the pulse this way, right?
Yes.
And then the pulse came back this way. And then it went back this way, and then it went back that way.
So is one trip considered to be one wavelength?
This is the length, the 38 feet is from here to here, and there's no wavelengths here because it's not periodic. It's just a pulse, okay? So this is L.
Okay.
All right, there's no, you only talk about wavelengths when you have a periodic wave, all right? So this is just a pulse, and we sent the pulse, and it went back and forth, et cetera, all right?
Oh, do we want 38 times 4?
I would be happy to write it if you would tell me.
152.
Okay. All right, and then when you switch 152 into meters, you would get 46.34. And then someone averaged all the times and got 2.44. So our total distance and our total time are known. Therefore, our rate is 20-something? 19-something? Anybody got an answer for that one?
Hold on a second. 18.99.
So 19 meters per second. So, if on the AP exam they gave you a short procedure answer question on a lab, and they said, you're given a spring, a string, a wire, or something, and you want to determine the speed at which waves are transmitted along that string, spring, wire, whatever. This is a reasonable method. Yes? Okay? Now, why in this diagram did this wave, the first wave came in, and I sent the second wave back, why did, because when it comes in, it's going to look like this, right? Yes, no?
Mm-hmm.
When it's come. So why here did I invert it? Because it's a fixed end. Alright, so if you had to draw a diagram, you would probably include that fixed end concept. All right? Are you good so far? Yes? Okay. Now, if you had a reasonable source of error, what do you think it would be? Don't say timing. All right.
Like sprung spring.
So, is the speed in this part of the spring the same as the speed here?
No.
No. Is it the same as the speed in this insane part right here? No. Is it the same as the speed in this part here? No. So, if your medium is not completely uniform, right? And in most long springs, you do get craziness like this because things get sprung, they get twisted, they get contorted, so that we might not have a real uniform medium, all right? And that would mean that we're looking at more of an average speed. Well, actually, this is probably more of an average speed. Now, do you think the amplitude that Annie released it with made a difference?
No.
Even if there's a difference.
As far as the speed is concerned first?
No.
No. The amplitude does not change the speed, but it does change your ability to perceive where the pulse is, right? Okay. So the amplitude helps us see it, but she can release any amplitude she wants and we'll still get the same speed, right? And I think it is a better term when you're writing to call it average speed, because obviously it's not instantaneous. We have nothing to measure instantaneous speed with, all right? Okay, now you could say something about timing if you want, only in the sense that you have to make sure that the timing is done as best as possible, but that's always a goal in a lab,
So,
right?
if you were to say like the source of error is that the medium is not uniform, would you say like the spring had areas that were...
Had different spring constants,
Okay.
okay? If they give you a rope or a wire, then that excuse isn't going to work, because ropes and wires don't have different spring constants, all right? So ropes and wires, I think probably the only thing you could say maybe is timing, or the perception of when the pulse really reaches the end that you want to time at, all right?
Should we say that for an error?
I don't think on our lab it is that.
Okay.
I mean, I think for us it's uneven spring constants, all right? Are you good? Does it make sense to you?
It does. Is
Okay.
that the whole lab?
Now, what dear?
Is that it?
That's the beginning of the first one, yes.
Yes.
All right. Now, so the medium, and again, I want you to write
Uh-oh.
this 5 billion times. The medium controls the wave speed. So if she sent a standing wave down, if she oscillated like she was trying to when Sarah was counting, which I had to stop because I was afraid Sarah would lose her mind if she didn't, if she couldn't see the squares on the floor, all right? But if you set up a standing wave where you get the nodes and the antinodes, would the speed have been the same?
No.
Yes. Because the medium is the same,
Yeah.
okay? So the medium controls the wave speed. So if I send different waves down this spring, all those waves at that stretch, right, because we have to count 38 feet, all those waves would have exactly the same wave speed, if they were periodic or if it was just a pulse. You good? Yes? All right, into that one. All right, now, I have to set up this, but at least I've got it to say it does have a sound card, all right? So before we do this, you're going to look at waveform and vibration graphs, and I'm going to show you what we mean by that. And I might, this is bad for them, but let's see. What does it look like on the screen? Can they see something?
Let me check it out.
Okay. All I want to see is the shadow. Can they see that shadow?
Oh, we're good.
Stay there.
We are golden.
So we can see the shadow? Yes, no?
Yes.
Okay. Now, I am very bad at focusing things because my eyes don't focus anyway. Is that cleaner? Is that a good clean?
I
Alright.
think so.
Then we'll move this over to this side. How about moving this up just a little? I want this to be flat.
Yeah, I do that.
Look and
Alright,
Justin.
how do we look? Good?
Look pretty good.
Alright, now, I want my pen to represent a position, okay? Now, for that position, I can move the wave in and out of the position,
Wow.
and what does the position do? It just bobs, right?
Mm-hmm.
Because the position in the wave just travels the wave's crests and troughs. Are you good? I think I should be going the other way because I think I'm unscrewing my screws here, right? But regardless, it's not the position that's changing. It's as the wave passes that position, it's the height of the wave. Are we good? Do you see that?
Mm-hmm.
All right. So, this is called a waveform graph. It tells you at one moment in time what the position of a particle is. All right? Now, at a later moment in time, I think I've totally done this wrong, but at a later moment in time, then it might be in a crest. Or in a later moment in time, it might be in a trough. But if you took a picture right this minute, I guess we'll leave it at a crest, all right? Then it's located at a crest. So what a waveform graph does is tell you at one moment in time where a certain molecule, particle, piece of debris, boat, plastic, whatever, where it's located, okay? So this is an example of a waveform graph. Good? All right, now, so if I had that waveform graph, do these write on this stuff?
We can find out.
I think
Pretty
it
sure.
does.
I remember from
All
back
right,
in the
so-
first grade.
Oh yeah, we used them for fix-its.
All right, so let's say that this is equilibrium, and that was where my, oh shoot, you don't see anything.
Try a
Oh,
Better,
that doesn't.
worse,
try a dark. Do you have a?
better,
It's
Oh,
getting better.
ooh,
better.
that is nice.
Is that good?
That is nice.
You
All
sound
right.
like that doctor.
And we can sort of see, yes? All right. Now, if I then took another graph, and I guess I can do it here.